Have you ever just stopped and looked at the world around you? I mean, a glass of water, the chair you're on, the air you're breathing, and just wondered, what is all this stuff really? What's the secret that connects it all? Well, that's what we're diving into today. We're peeling back the curtain on the hidden world that runs literally everything. I mean, just look at this. It's incredible. In this one single powerful shot, you've got the three main states of matter all together. You've got the solid rock, totally unmoving. You've got the liquid water blasting upwards. And then you've got that billowing steam. That's a gas, just disappearing into the air. So they're all right there, but deep down, what's the real difference? How can the exact same stuff, water, show up as solid ice, liquid water, and then invisible steam? That's the big question we're going to crack open. Okay, so first things first, let's start with what we can actually see and touch. We sort stuff into categories based on properties we can observe every single day. This table really lays it all out. A solid, it's got a fixed shape, a fixed volume, and knows what it is. A liquid, though, is a little more go with the flow. It'll take the shape of whatever you pour it into, but it keeps the same volume. And then there's gas. It's kind of the wild card of the group. It takes the shape and the volume of its container. It just expands to fill up any space it's given. And that right there is why you can compress a gas, but you really can't with a solid or a liquid. And you see this everywhere. It's not just in dramatic geysers. Just think about a cafe. You've got the solid ice cubes clinking in a glass, the liquid orange juice sloshing around them, and the gas, the steam, puffing out of the espresso machine. It's the exact same science, just a little cozier.
All right, so we get the what, we know the properties, but to understand the why, well, for that, we have to zoom in. No, I mean way, way in. We need to explore the secret life of particles.
And that brings us to a huge idea in science, the kinetic particle model. It's actually a pretty simple concept, but it is incredibly powerful. All it says is that everything, everything, is made of tiny little particles. And here's the kicker. Those particles are never standing still. They are always moving, constantly and randomly. This diagram just explains it all perfectly. Look at the solid. You see how the particles are packed in super tight in this neat, orderly pattern? They can't really go anywhere, so they just kind of vibrate in place. That's why solids hold their shape. Now, in the liquid, the particles are still pretty close, but they have enough room to slide past each other. That's what lets them flow. And then look at the gas. The particles are super far apart, buzzing with energy and just shooting around randomly at high speed. And that, my friends, is why a gas will always expand to fill its container. So, hold on. If the only real difference between these states is just how the particles are arranged and how much energy they have, well, that must mean you can change a substance from one state to another just by adding or taking away energy, right? And of course we can. We see it all the time when ice melts into water, or when you boil that water and it turns into steam. And it goes the other way too. When steam cools down, it condenses back into water. And when that water gets cold enough, it freezes right back into solid ice. These are the phase changes that are happening all around us, all the time. So what's happening on that tiny particle level? Well, it's basically a four-step dance. 1, the particles suck up heat, which is just energy. 2, that extra energy makes them vibrate or move around way faster. 3, they start moving so fast and so violently that they begin to break the forces holding them to their neighbors. And 4, once those bonds are broken, bam, the substance changes its state. That's how the vibrating particles in ice break free to become flowing liquid water. Okay, this is all a really great story. It's a very neat theory that explains everything we see. But it's all happening on a totally invisible, microscopic scale. How on earth do we actually know that it's true? That's the kind of question a good scientist always asks. We have this really elegant model, but where's the hard evidence? Is there any way to actually see this random dance of particles? Turns out there is. And the proof has a name: Brownian motion. It's what you see when you look at slightly larger microscopic things, like specks of pollen or dust, floating in water or in the air. You see them jiggling around in this totally random, jerky way. And why? Because they're constantly being slammed into by the much smaller, totally invisible particles of the fluid around them. This is how we can actually watch it happen. If you look at smoke particles under a powerful microscope, you can't see the air molecules themselves. They're way, way too small. But you absolutely see their effect. You see the bigger smoke particles getting shoved and knocked around. moving in this chaotic zigzag path. Every single turn is because it just got bombarded by a bunch of unseen air molecules. This is the smoking gun. It's visible proof of that invisible world. So now that we have actual proof that our model is real, let's use it to understand something we deal with all the time, but maybe don't think about this way: gas pressure. What even is pressure, really? It's not some weird, mysterious force. It's just the combined effect of trillions upon trillions of tiny gas particles constantly smacking into the sides of their container. Each little collision is tiny, but add them all together, and you get a constant, steady push. That's pressure. Okay, so what if we heat up that gas? Well, the particles get more energy, which means they start flying around a lot faster. So they're going to hit the walls of the container more often, and they're going to hit them with more force. More frequent, harder collisions, that equals higher pressure. It's exactly why you never, ever leave a can of hairspray in a hot car. And what about volume? What if you take the same number of particles and squish them into a smaller box? Well, now they've got less room to move around, so they're naturally going to slam into the walls much more often. And we just learned more collisions means higher pressure. It's totally intuitive once you picture those little particles bouncing around. So at the end of the day, here's the big takeaway. From the fixed shape of an ice cube to the pressure inside a balloon, it all comes down to the same fundamental truth. Our entire physical world is run by the constant, chaotic, and completely random dance of these tiny, invisible particles. It really makes you think, doesn't it? We've just pulled back the curtain on one layer of reality that's hiding in plain sight. And it just begs the question, if this whole invisible world of particles is running the show, what other unseen forces and hidden principles are out there, quietly shaping the very fabric of our universe?